So sound can travel through many different materials. You can have sound traveling through gases, liquids, solids. So sound travels through the air, sound travels through water, sound travels through any kind of solid material you want. And it does so at different speeds. In general, the speed of sound traveling through a material depends on how elastic the material is, like how easily it springs back together. The more elastic, more springy it is, the faster the speed of sound is. And it also depends on how heavy or how much inertia the material has. So this is kind of generally true no matter what the material is. And for solids, liquids, and gases, we have different ways of measuring these elastic properties and inertial properties. For a solid, this elastic property is called Young's modulus. And the inertial property is the density of the material. We use Greek letter rho to represent density. So if you want to know what the speed of sound is in any solid material, you go look up the Young's modulus for that material, you look up the density, and now you can calculate it. Similarly for a liquid, there's a property called the bulk modulus. And again, we use the density. You can look up the same thing for gas. Two other common applications that we'll be using in this class that you see quite a bit in physics are when you have a string under tension, like a guitar string. How fast does the wave travel back and forth in that string? Well, for strings, the elastic property that's important is the tension. And the inertial property that's important is the mass density, the linear mass density, and we use the Greek letter mu for that. These are volume densities. How much mass there is per volume of solid or per volume of liquid or per volume of gas. This is a linear mass density, how much mass there is per length, like the number of grams per meter on the string. So T is the tension force that the string is under, and mu is the linear density. Or mass per length. And finally, there's one more important equation that's kind of separate from these. It's for the speed of sound in air. You can also use this equation for air, But with air, we also commonly want to take the temperature into account. And we have another equation for that. So in air, we're going to say the speed of sound is 331 meters per second times, now be careful of my notation here, T for temperature, divided by 273 Kelvin. Again, we only have so many letters to use, and just keep in mind if you're doing strings, this T is for tension. If you're doing air, this T is for temperature. I think the textbook uses F instead of T in this equation. So two common temperatures at 0 degrees C, the speed of sound in air is 331. And at 20 degrees C, which is about room temperature, the speed is 343 meters per second. And this number, 343, you can often assume that that's what the speed of sound is if the problem doesn't tell you otherwise. If it doesn't specify a temperature or anything, you'll usually just assume that the speed of sound in air is 343 meters per second.